でもですか。Okay, let's start. Today we will talk about deep dive into OpenStack private cloud upgrade challenges for enterprise users, fix issues and fixes. So before we begin, let us quickly introduce ourselves. My name is Kota Asai. I'm here today with my colleagues with Inokuchi, Kazuma, and Isato, Matsushita. We are on the same team and we are responsible for developing and operating the virtual machine infrastructure for our cloud, OpenStack cloud. In this session, I will start. Kazuma will continue with the next part, and Isato will conclude our presentation. Okay, here is agenda. First, we will briefly introduce our company and our cloud platform. Then we will move on to the main topic, the problem we faced in the upgrade process. And finally, we will wrap up with a summary. Our company, NTT Docomo Business, is core part of NTT Docomo Group. We provide a wide range of services from ICT infrastructure, cloud platforms, and solutions. We provide these not just individually, as integrated solutions. This supported is by our major global resources, such as Tier 1 global net internet backbone and data centers in over 140 countries. Our cloud services is called Smart Data Platform Cloud. It's built on OpenStack, and we launched it in 2016. And so it's been almost 10 years. We have 8 regions, and SDPF Cloud is one of Japan's largest cloud platform. This slide shows an example of tenant environment. In this project, we provide basic services on servers, storages, and networking. In this presentation, we will focus on these virtual server services. We have upgraded our OpenStack version twice. First, from Juno to Mitaka, and then upgrade from Mitaka to Queens. In this presentation, we will focus on 3 key problems we explained during the Queens upgrade. First, virtual machine high availability problem. Second, Windows link, and the final, memory problems. From these experiences, we learned valuable lessons that can be applied to different phases of development lifecycle. We will share on our overview of each problem, how we solved it, and the lessons we learned. Case 1, virtual machine high availability problem. Are you familiar with pet with cattle analogy for cloud resource management? In this pet model, we treat our resources like household pets, nothing them, back to health when they fail. In the cattle model, resources are managed as a herd, not individually. And why the cattle model is often ideal in the cloud. Our customer tends to treat their resources like pets. This means they expect their resources to be continuously up and running. For them, virtual machine high availability, which requires instances from host failures, is extremely critical service. To meet their expectations, we operate our infrastructure to maintain a high quality of standard. Specifically, we have service level algorithms that state a single instance downtime must be less than 10 minutes. Our hypervisor hosts up to 230 instances per node. So when a host fails, we need to evacuate 230 instances within 10 minutes. The problem in case 1 occurred while we are in the middle of testing to verify the quality standard. Okay. For virtual machine high availability, we use OpenStack Massacre. It automatically recovers failed instances using 3 key services. Massacre host monitor runs each node on every computer node and detects host failures and sends notifications. Massacre API receives the notifications and triggers the engine to take action. Massacre engine calls Nova's evacuate API and move instances from failed host to another healthy one. After upgrading OpenStack to Queens, we face the serious problem. The evacuation of 230 instances failed to complete within 10 minutes. This meant we could no longer meet our service requirement. We investigated and found the direct cause. The massacre process failed due to a timeout. The root cause was that the instance boot time exceeded Massacre's 90-second evacuation timeout. When the Massacre engine calls evacuate API, the Nova compute on the destination host eventually perform a level of instance. After Nova compute, prepare and create the instance. It was received a VFI private event from the network controller. By checking the logs, we found that Nova Compute was waiting for the third VFI private event, which is 300 seconds, to confirm network availability. After an internal discussion, we learned that our network controller is designed not to send VFI private event during the evacuation process. And this means Nova Compute should always wait for the full timeout period. Even with this behavior, the evacuation process in OpenStack Mitaka incorporated within 10 minutes. However, due to a behavior change in OpenStack Queens, it now takes longer than 10 minutes. At first, we thought we could just extend the timeout value, but it wasn't that simple. With the existing configurations, the math showed that we could only evacuate about 3 instances within 10 minutes, in 10-minute window. This was far too slow. So we had to find a way to evacuate 230 instances and in under 10 minutes without increasing timeout value. Ultimately, we adjusted 3 parameters to solve this problem. First, we reduced VFI private timeout from 300 seconds down to 90 seconds. For this problem, we also considered modifying our network controller to send VFI private events. However, we didn't have enough time, so we decided to change the timeout value instead. At the same time, we increased Massacre's evacuation timeout from 90 seconds to 150 seconds. Together, these 2 changes solve the timeout error. Next, to speed up the evacuation process, we increased the number of Massacre's parallel processes. Increasing this number adds more load to authentication system, including Keystone. So while monitoring the load carefully, we increased the parallel execution value from a default 3 to 150. By combining these changes, we can now fully evacuate 230 instances in under 10 minutes our SLA. Okay, lesson done. There are two lessons we learned from virtual machine high availability problems. First, upgrade can have unexpected side effect. For example, performance can suddenly change. This experience reminded us how essential testing is after an upgrade. Second lesson, check the configuration file first. A change in configuration file can often solve the problem without touching code. Okay, through this experience, we identified some challenges in Masakai's architecture. So, and we want to improve the overall virtual machine high availability experience. We studied by submitting a patch, which was our first step in contributing back to the community. Thanks. Let's move on to the next problem.
I'm Kazuma Inokuchi. In this case too, let me introduce a new program, network interface card program. We encountered with Windows VMs. The background for this program is a project to upgrade compute nodes. This was a main upgrade project, including major version changes. Major version changes for almost all software components, like host OS, kernel, QM, and libvirt. In this presentation, we'll refer to the old version compute node as CPV2. This is compute version 2, and the new version as CPV3. As an enterprise-grade service, it is essential to address a wide range of customer requirements. In addition to Linux distribution like Event or Dell, there is significant demand for Windows Server. So, consequently, for this upgrade project, it is a critical requirement to verify that non-Linux OS function correctly and without issues. The incident in case 2 was discovered during performance testing on the new platform. This performance test is part of our non-functional testing, of course conducted after functional testing. During the test, a script we have used to automatically change the MPU size failed because throwing an error at this point. That is, it couldn't find the target network interface. We checked the interface status and confirmed that the nickname recognized inside the VM has changed from the Ethernet to Ethernet interface 0. And further investigation revealed a more serious problem. Consider a scenario as shown in like this. As part of upgrade operation, a VM is created on the old platform, is migrated to the new platform. At this point, the nickname is still Ethernet. However, the problem occurred when the VM on the new platform is rebooted. We discovered that not only the nickname renamed, but it itself was recognized as completely new device. As a result, the original NIC settings were lost, and the VM with static network configuration become unable to connect the network on the new platform. So, for device recognition, Windows OS manages and caches two distinct identifiers. The first is hardware ID. That is composed of elements like vendor ID and device ID and so on to define the specific type of hardware. The other is device instance ID is derived from information reported by the bus driver, such as bus ID or slot number, to specify the device's location. In case 2, a post-rebooted analysis revealed the following. In case 2, hardware ID were not changed. This means device is identified as the same hardware model. However, device instance ID were changed. And that is, the system detected the device at a new topological location. As we continue to investigate for a solution, this problem was related to the VM's virtual chipset in the old and new platform. Both were using PCI 440FX, but the version indicated by suffix was different. Then we discovered a workaround applicable to OpenStack Nova, that is using system metadata. Unlike common metadata, system metadata is cannot be modified by users and is for administrators only. We found that by setting the masking type key here to the same value as the old platform, PCI 440FX type A, then we could lock the VM's virtual chipset on the new platform. After applying this change and rebooting the VM, we confirmed the NIC name remains Isato, and the original NIC setting were preserved. Based on this incident, I'll explain the countermeasures we are prepared for our next upgrade project. We developed an automated validation tool for what we call virtual hardware. That is the hardware information as seen from inside the VM. This tool, based on this VM operation scenarios we created, retrieves virtual hardware and compares it with the previous step. The final report, like this, details which operations causes changes, and those differences are helping us detect problems quickly. Finally, I'd like to share the lessons we learned from this incident. First, when should we have discovered this problem? As I mentioned, we first noticed the problem during the performance testing. However, the root of the problem occurred in the VM migration and reboot phase. So this means we failed to maintain sufficient VM compatibility.
One document dropped.
A fundamental requirement of the upgrade project, of course. The late discovery also left us with little time to fix root causes. So, forcing us to take the compromise of locking the virtual hardware. This clearly demonstrates the need for a shift-left approach in software testing. By moving problem discovery earlier, like this, or to the left on the development timeline, we can address issues at a much lower cost. Second, our testing perspective was incomplete. We can look at this issue from two main viewpoints. First, we didn't have a high enough resolution or detailed understanding of our agreements. If we had been tracking the detailed virtual hardware information, we would have found this issue more quickly. Second, our test coverage of the VM lifecycle is insufficient. It's crucial to imagine the actual scenario our customers might encounter and incorporate them into our testing. The case 2 is concluded here. The next is the final case.
Thank you, Kazuma. Bonjour. I'm Isato, and this t-shirt is best t-shirt in the world. Okay, I'll talk about final problem. So in SAP Cloud, in addition to standard IaaS virtual machine, we also provide virtual network functions VNF. This runs on OpenStack Nova computers, nodes without distinction, and we treat customers' VM and our VNFs in the same way. After we upgraded to the Queen release, the NFV teams reported degraded performance. This figure shows ICM echo latency. Latency for VNF. It continued to rise after the upgrade. Following this report, we started to investigate what happened. We noticed that memory usage was ballooning on several compute nodes after the upgrade. It kept growing about 5 GB per day. Since this behavior began right after the upgrade, the most likely cause is the delta introduced by the upgrade. The difference before and after the upgrade were replacing Masakai host monitor and Nova compute and containerizing libvirt and vSwitch2. We suspected that one or more of these changes might have been responsible. We checked which process was driving the higher memory usage, and we did not find any leaks of normal growth. We then looked at the memory by categories, comparing before and after the upgrade. The increase was SR claim. SR claim is part of the kernel slab cache. The slab cache is consists of S reclaimable and SR reclaimable. S reclaimable can be reclaimed by drop cache, however SR reclaim cannot. Therefore, SR reclaim can store used memory, and it does not appear as user space process memory because it is owned by kernel. We found the clause by stopping each process in turn and comparing the rate of memory growth. That the issue was cron job that periodically invoked vSwitch tools. The tools manage the vSwitch tool and containerize it as part of upgrade. Every time the cron job runs, it will execute Docker run because we containerize the tool. I will cover this later, but the certain kernel version the single handling used by container is unstable, which lead to instability around the slab cache. By this point, we knew why SR memory was growing. The remaining question was the ICMP echo latency. The key was our monitoring of proc slab info. Each time we need proc slab inf with cat command, the kernel scans the slab cache and temporarily disable interrupts. The larger the slab cache, the stronger the effect. In our environment, as SR reclaim kept growing after the upgrade, those lead to longer and ICMP echo latency increase over time. To solve this issue, we implemented two solutions. First, as a mitigation, we disabled the offending cron jobs. In our environment, we do not need to output continuously, so we stopped it immediately. Second, as a remediation, we eliminated the root cause by adjusting specific Linux kernel settings. I will explain those changes on the next slide. As a remediation, we added to see this option to the kernel command line. This parameter disables kernel memory accounting. On older kernels, this feature can be unstable, but disabling it is now workaround for container-related issues. We need to reboot the computer node for this take effect. We knew how to fix it, but at our scale we needed careful rollout. About 1,000 hosts had to be rebooted. We repeated 4 steps until all nodes were covered. First, we applied remediation the reserved compute nodes we kept for virtual machine high availability. Next, on every compute node, update grab config with new kernel parameter and hold, waiting for reboot. Thus, when a node external VM crosses the threshold, run live migration, move all VMs from that node to reserved node. Finally, treat it as a new new reserved computer node. We cycle through these 4 steps until every computer node was completed. So we learned 3 key lessons from this problem. First, dog fooding and measurement on real workloads. Before a new release, we run many tests, including functional tests and performance tests. These tests cover a lot in single controlled environments, but in IaaS, we must support many kinds of customer VM workloads, and some cases cannot be pre-tested ahead of time. To make that area so small as possible and catch issues early, it is important to coding with real workload and correct their key metrics. Next, unexpected behavior changes. Small changes at the application layer led to system-wide impact. On each computer node, the OpenStack service, monitoring agent, and customer VMs all run on the same Linux kernel. As engineer, we need to keep that in mind. In release testing, we should look beyond future correctness and watch for subtle behavioral shift as well. Finally, automated live migration for enterprise grade availability. Some kernel fixes require reboot. So to keep availability in those cases, live migration must be highly reliable and low cost to run. By automating live migration and coordinating it with host configuration changes, we can handle a wide range of issues and improve overall reliability. To close, I'll summarize the 3 issues, the key lesson we learned. First case, we handled a design stage problem. We tuned massively to meet the SLA target for VMHA evacuation time. OpenStack has many settings and it is built to be adjusted. When a problem shows up, try configuration tuning first. With careful tuning, OpenStack can solve specific issues even in enterprise environment. Case 2, we handled a unique device problem. In cloud infrastructure, shift left approach help you fix issue earlier and at a lower cost. In design and implemented tests to cover real user use case. Check that required guarantee and met and run validation early in development cycle. In case 3, we showed how small changes at the application layer led to system-wide impact. To catch the issue like this, we need to do coding and production-like monitoring during testing. And to increase the problem we can handle without downtime, automatically navigation is essential. That's all the time we have for this session. Please scan QR code on the slide or find me afterward if you have any questions. Thank you for attention.